So we did this implicit derivative. I'm going to go ahead and plug in this point, and I'll get the slope at this point. I think that's what I'll get, right? The x is a -3. That's going to be -36. 8 times y there, that's going to be 16, right? Because y is 2. Times dy dx equals 0. Anyway, now I'll solve for dy dx. I'll move the 36 over. I'll divide by -16. So there it is, 36 over -16. Or 9/4, -9/4. Or you could call that -2.25. Some of us like fractions. But I did it in the implicit derivative. I went ahead and plugged in my point kind of early because I had a point to plug in. I still had to solve for dy dx to call this. This number is now called the slope. Thank you, thank you, thank you. I know some of my questions are obvious. They're so obvious. But, right, that's the slope.
Now you use point slope.
Now, I have a point. Do I have a point?
Yeah.
I have a slope. If I have a point and a slope, I can do what they wanted. Don't forget, what they wanted was the equation of the tangent line. So, I'm going to do my y minus my y value equals my slope times x minus the x value. You know, once you find the slope and you have a point, you can get the equation of the line, equation of the tangent line. I'll just distribute and clean this up. -9/4 x, that's a +3. When you multiply it, it'll be a -27/4. When I add this to, I guess I'm adding an 8/4. And so I love fractions. I like messing with these fractions. Here I am with whatever the hell that is.
19/4.
Thank you very much. That's the equation of the tangent line.
I did it the other way.
Well, did you get it right?
I got it right.
Well, what do you mean the other way? What do you mean by that?
The other way we would have to like
Solve this for dy dx?
yeah,
And then plug it in?
Yeah.
That's
I mean,
what I did too.
I can solve this for, right, because that's what I've been showing you, I'm sorry.
Right,
Oh,
yeah.
but you can solve for dy dx and then plug in your point. But hopefully you get my point, which is
You could do it.
you can plug in the point and then solve for dy dx. But, hey, you know what? I kind of want to draw this for you, but I don't, this is kind of a weird one. With that minus sign, if that was a plus sign, this would be a beautiful ellipse. And earlier you saw me do a circle. So, you know, we can do these. These are things that have an implicit relationship. These are things that aren't functions. Circles, ellipses. This one happens to be a hyperbola of some kind. I don't really, I'm not quite an expert on hyperbolas, but I think, you know, roughly it might look like this. That's how hyperbolas kind of look. Where am I at? I'm at this point, -3, 2, which maybe I could say is roughly there. This is very rough. This is very rough, but I think that thing's a hyperbola. I think it looks like this. It's not a function. I think I'm at that point, -3, 2, and I just found the equation of the tangent line. And if I drew that, if I typed that in my calculator, I would get this graph. And hopefully it would have, you know, it has a negative slope. It does have a negative slope. It has a y-intercept at -19/4. I mean, hopefully this is rough, but it's rough, but it's fairly accurate. What's funny is you can't type this into your calculator because how do you type something into your calculator? You have to have y equals.
So
How do you get y equals? You got to solve for y and make it explicit.
Right.
Which requires a square root and a plus and a minus. Anyway, it's kind of nasty, right? But if you wanted to sketch it, you'd have to kind of do that, I guess, using your calculator. But I just wanted to quickly interpret it for you. It is a graph, and we just found the slope of the equation of the tangent line at that point. All right, so, man, I don't know what else to say. Here, what about this one? What about this one? Can you do this derivative, please? I would call it implicit. I mean, my brain, so you got this new thing now. You look at these things and you say, oh, shit, that's implicit. I mean, all the x's and y's are mixed together. It's implicit, and I need to take on that approach. So I walk into this, but because he's an x term, it's just 2x. Right? What about now? Good. Listen, this slips by a bunch of students on a test day. It slips past them. This is a little product rule right here. I mean, we're in this world where x's and y's are different, and x times y is a product rule. I have to treat x as its own function and y as its own function, I guess. So it's a little product rule. Here we go. Here's how you do it. By the way, it has a minus sign in front of it, which makes me want to put it in parentheses. I'm worried about that minus sign distributing, so I'm going to put this in parentheses. Here we go. A little product rule. Derivative of the x. 1. Write down the y. Okay. Plus, write down the x, and take the derivative of the y. dy dx. Dude, awesome. Little baby mini product rule. Let's keep moving here. Plus the derivative of him, please. Awesome. Thank you, guys. Equals the derivative of the other side. Yes. That's awesome. That was a little product rule in there. Those things are product rules. X's times Y's. So again, I'm so happy you got that right. I mean, I'm happy. But there's more work to do. You're supposed to solve for dy dx. It's this algebra now. It's algebra. I'm not going to do much here except distribute that negative sign. Negative y, negative x, dy dx, plus 2y dy dx. The algebra usually is this. All the terms that don't have a dy dx should go to one side. All the terms that do have a dy dx stay on one side. And then you factor it out and divide. I mean, that's the procedure of solving. That's the algebra that tends to always happen. So I'm going to leave these guys, this dy dx stuff, I'm going to leave it on this side. And what am I moving to the other side? I'm going to move this over. It's a negative 2x, and it's a positive y when it moves over. And then I'm going to factor out a dy dx. And that leaves me with negative x plus 2y equals negative 2x plus y. Right, you guys? Factor it out, and then divide by that junk, and you're done. Your derivative, dy dx, is, this implicit derivative is that negative 2x plus y over negative x plus 2y. And your derivative itself, which is just a formula for the slope of the tangent line, it's sitting there. If you had a point to plug in, you need both coordinates. You need an x and a y coordinate. You could plug it in and get a slope at any point. You need an x and a y coordinate, but you could plug it in and get the slope at any point. Okay. Watch this. Are you ready? This is it. All right, here Here you go. Your brain has to work here. You ready? Now I want to find the derivative of y with respect to t. Check this out. We just stepped it up a notch. I want to take this derivative with respect to t. So the variable is t. Now I know it ain't there no damn where. I know it ain't. By the way, let's pretend it was. Let's pretend there was a t over here. How would you do the derivative with respect to t of a t squared? How do you do the derivative with respect to t of a t thing? 2t? Yeah. How do you do the derivative with respect to x of an x squared? 2x. How do you do the derivative with respect to t of a t squared? 2t. Yeah. When the variable... Okay, but there ain't no t squared. So I'm doing the derivative with respect to t, and there ain't no t's in here. See, how do you do the derivative of a y squared when you're doing it with respect to some other variable like x? You do 2y dy dx. And so how do you do the derivative of x squared when you're doing it with respect to t? 2x dx dt. That's what you have to do when the variable doesn't match. When you're doing the derivative with respect to t, the variable doesn't match, you have to do this extra little dx dt. What now? I'm doing this y variable, but I'm doing it with respect to t. So how do I do it? 2y dy dt.
Equals 0.
And that's a 0. Okay. I said I wanted to find dy dt. That's not really what I wanted. I really wanted the derivative of this whole expression with respect to t, which is this. Do you have a question? Look at this. This is a equals pi r squared, right? Pi is a number. Pi is not a variable. Pi is a number. I want to do this derivative. I want to do the derivative of this equation implicitly with respect to a variable that ain't even up there. I want to do the derivative of this with respect to t. So when you run into the a, how do you do the derivative of an a with respect to t? dA dt, is that what you said?
Right.
Good. How do you do the derivative of a y with respect to x? You dy dx. How do you do the derivative of an a with respect to t? dA dt. I want to do this derivative with respect to t. The variable is r, and I probably should bring the 2 down. The pi is a constant. Let's leave the constant there. And then you bring the 2 down, 2r. And now I'm doing the derivative with respect to t.
dr dt.
dr dt. Damn, you guys are good. We're doing the derivative. We're doing an implicit derivative with respect to a variable that ain't even there. But that's good. That's awesome. See, what I just did was I just leaped into a section called 3.7. And the title of this section is Related Rates. And so what we have here is related rates of change. I mean, when I decided to take this derivative with respect to t, what I have is the rate of change of the area with respect to t, and how does that relate to the rate of change of the radius with respect to t. I have a rate of change, I have 2 rates of change that are related. I have related rates. Are you okay? I have a rate of change of area with respect to time, and I have the rate of change of the radius with respect to time. See, this first off, so I was trying to get you to learn the mechanics of taking the derivative with respect to some variable that ain't even there. But the reason we're doing this, let's get to the point. The reason we're doing this is up here in 3.7 with these related rates. This is what we do. Listen, it's full of these word problems. These word problems are relating these rates. Here's what's going on with this problem. With this problem, the classic word problem, they write up all kinds of word problems, but a classic word problem is, you know, some oil tanker is spilling oil in the Gulf of Mexico. And that oil is spilling out of the tanker, and it's forming a circle right on top of the Gulf of Mexico. And it's spreading, right? Because oil's pouring out, so it's spreading. And maybe it's spreading at a rate of, maybe we say that the radius is spreading, is growing. Watch this. The radius is growing at a rate of, there's a lot of damn oil. Maybe I'm going to say it's a big oil tank. The radius is growing at a rate of 50 feet per second. Shit, that's pretty, that's bad. Maybe it should be 50. Maybe it should be 50 feet per minute, but it doesn't. Let's just go with this. The radius is growing, so you're spilling oil. So what we have is this changing environment, right? We have a circle. We have a circle whose radius is growing. If the radius is growing, therefore the area is growing. The question is, at what rate is the area growing? Here's the question. So we set up these word problems like this, and then we ask this question. At what rate is the area changing at the moment when R is 300 feet? So now look at these words. You read these word problems, and I did a sloppy job up here, but I'm doing a good job. Sorry, but it's just written kind of sloppily. Look what they're asking for. At what rate is the area changing? Are they asking for the area? No. They're asking for the rate of change of the area. And what they mean, by the way, is with respect to time. I think all these problems are with respect to time. So that's why I did this derivative with respect to t. But I think they're asking for dA dt, don't you think? You got to read this and understand. They're asking for the rate of change of the area with respect to time. So they're asking for dA dt. And we were given this. They want this dA dt at this moment in time, because it's, you know how these derivatives are. They're changing every damn second. So they want it at this moment, when the radius is 300. The radius is changing, by the way, too. That was given, too. The radius is growing at a rate of 50 feet per second. What did they just give me there? Thank you. Thank you. This is not the radius. This is the radius. The radius is 300. But what this is the rate of change of the radius. And that is, she said it, what'd she say? dr dt. So they gave me dr dt is 50 feet per second. So they gave me the rate of change of the radius. They asked me to find the rate of change of the area when r is 300. Now here's my job. I have to read this problem and come up with an equation that, what's going on? This oil is spilling into the Gulf, and it's forming a circle. So I need to come up with an equation for a circle, the area of a circle. Okay, I did. You with me? Then it's my job, after I come up with that equation, then it's my job to take the derivative implicitly with respect to t. And that's what I made you practice doing. You ready? You did that, didn't you? You took the derivative of him with respect to t. You took the derivative of this with respect to t. You with me? And now you can use this to answer the question. See, now you have these related rates, and you can answer this question using this. What's going on? They're asking for dA dt. I got pi times 2 times the radius. What's the radius?
300.
300. And I got the dr dt. What's the dr dt? That's the 50. When I multiply this together, it's a huge number. It's 30,000 pi. 30,000 pi? 3,000? 30,000 pi. 30,000 pi feet squared per second. I think that's the units because it's a, look, it's an area over time. It's an area over time. I could have, sometimes I could have kept track of my units a little better. Look at this. What are the units on this 300? What was this 300? That was just feet. What was the units on this 50? Well, that was feet per second. There is no units on these numbers, so when you multiply these units, it's feet squared per second, which is what it's supposed to be for an area.
Oh, feet squared, yeah.
Yeah, square feet, feet squared. Hey, by the way, what is, if you put the pi in there, I mean, that's pi is 3.14 up times, and then it turns into 90, what is it?
9,47247.77961.
All right, feet squared per second. Okay, so that's the actual, I mean, there's the number. It's 30,000 times pi. It's, there it is. 94,000 square feet per second. Holy shit, that's spread. I mean, that's, the area is spreading big time. The radius is going 50 feet per second. I guess the radius is constant. 50, I got this circle, and it just keeps growing 50 feet every second. But when you go 50 feet every second, you're adding to the area. I mean, your radius is just going 50 feet, but you're adding a ton of area, aren't you? Right. Right. So that radius is growing at that rate, but it results in a huge rate of change for the area. You guys, I taught you implicit differentiation in 3.5, and there's good problems in 3.5, but I quickly got to the point here where, I mean, you really need this implicit differentiation concept here in 3.7 when you do these related rate word problems. They're cool little word problems, but they involve some equation that you take the derivative of with respect to t. And there's usually no damn t anywhere in there. So you got to learn how to take the derivative of these variables with respect to t. Let's just do another classic. Let's do another classic, and then I might just let you go early here. I might not get into 3.6. I might have to come back to 3.6. But let's do another classic problem. Here's a classic problem. You know, there's a barn here. There's a ground. This is the ground. This is a barn. See this barn? Anyway, you know, I like to paint the barn. I'm on this ladder. This is a 25-foot ladder. Okay, and I'm painting the barn. I'm up there painting the barn. You know. All right, and then one of my students, damn practical joker, he comes up and he grabs the bottom of the ladder and starts moving it this way at 4 feet per second. And I'm up there going, holy shit, you know, I mean, actually he's pulling the ladder away from the building. What am I doing then? What's happening to me?
Falling.
I'm falling down the building, right? Do you understand that? The ladder remains constant, 25. The ladder's not going to change length. So when he pulls this away, I'm falling down the building. Actually, that might be cool for painting. I could just hold the roller. He could pull me away. And then he has to push me back up. I don't know if he could do that. But anyway. Here's the question. He's pulling me away at that rate. The question is, at what rate is, I mean, this is the top of the ladder. These things can be a little wordy. At what rate is the top of the ladder moving at the moment. See, when we ask you this question, we have to give you a moment in time. So at the moment, it is, that's the ladder, 10 feet above the ground. Now, what was also given was this, the fact that he pulls it away at 4 feet per second. So this was given somehow in words. They wrote this up in words. They wrote this up in words. And now, good luck. So what am I teaching you here? I'm teaching you that we got a bunch of these word problems. And here's the first thing we need. The first thing we need is some kind of equation that relates these variables. Well, first of all, where's the variables? I mean, I got a good looking picture here, that might help, but I need to label whatever's changing and moving a variable. Whatever's not changing and moving maybe should be a constant. Like the length of that ladder, I don't want to call the length of the ladder a variable. The length of the ladder is 25. But what about this distance? Is it moving? Well, then I better call it x. What about the height that I am up on the barn? Is that moving? Yeah. Well, let's call that y. Is that okay? All right, so now you've got this kind of labeled here. There's a right angle there. Can you come up with an equation that relates these variables? With the oil spill problem, the oil was going out in a circle. It was up to us to read the problem and come up with that equation. With this problem, can you come up with an equation that relates those variables? Please. Please, please, please.
Pythagorean theorem.
Pythagorean's theorem, yes. Pythagorean's theorem. It's a right triangle, and from this picture you can relate these variables by saying x squared plus y squared equals 25 squared, or 625, right? That's the equation you need. And you got to come up with that, but you can. You're smart people. So you come up with that equation, and then you usually, this first step, I mean, you could think about what's going on in this problem, but usually what you need then, after you get the equation, is you need the related rates, which means you need to take the derivative with respect to t to get the rate of change of these variables. Like I did with the dA dt and the dr dt, so now I'm going to do it with this. Can I take these derivatives with respect to t, please? 2x dx dt. When you take it with respect to t, it spits this out like an implicit, yeah. Then what?
Plus 2y dy.
2y dy dt equals a 0, because that's a constant. Man, this is awesome, you guys. Now let me think. What was given over here? Hang on. What was given? What is this?
4 feet per second.
Yeah, what is that?
That's the rate of change of x.
That's the rate of change of x. Awesome, awesome. So you just said that dx dt is a 4 feet per second. Yeah, you're right. That's what that is. What are they asking for? What are they asking for?
Little ladders.
What rate is dy?
What is that? dy dt.
Yep.
They're asking for dy dt. Let me just make that note. This is me problem solving. This helps you guys. I'm getting organized. You see how this is me getting organized. They gave me that. They're asking for that. What else did they give me? At the moment when y is 10. That's what this says. So that's cool. I'm doing this at the moment when y is 10. So look at this. I got a lot of good stuff, but I don't think I got enough yet. Hold on a second. I mean, they want me to find dy dt. They gave me y is 10. They gave me dx dt was a 4. dx dt is a 4, right, you guys?
Right.
But what about this x? I need this x. I mean, if I'm going to solve for dy dt, if I'm going to solve for d, I need x. They didn't tell me x. They told me at the moment y is 10. At the moment when y is 10,
Oh, Pythagorean theorem. Yeah.
they didn't tell me x. Can I find x? Oh, sometimes the original equation helps you. Yeah. If y is 10, you can find x at that moment. So sometimes you need that original equation to help you get all the variables you need. Right. Using the original equation, when y is at 10, let's find x. This might not be pretty. But when y is at 10, I can find x. That's 100. That's 625. When you move the 100 over, I think it's 525. Yeah. And if you don't mind, I'm just going to call x the square root of 525. Okay. I mean, it's a decimal. And this is a word problem. Maybe I'm not. Maybe I'm a little more decimal friendly on a word problem. So that's x. It's a number. Well, I mean, what is it? 22, thank you. So when x is 10, when y is 10, x is 22 point something. Okay. All right, cool. So anyway, now I can find dy dt, which is the rate at which I'm falling at this moment. See, let's do it. What do I do? Move this numbers over? That would be 8 square roots of 525 all over 20. Did I just lose you guys?
No.
Okay, good, I hope not. I moved this stuff over and I divided by 20. And that's my answer. Go ahead and make it a decimal. What is it? 9 is...
What's 9.16?
Yeah, no, I did make one error. Thank you. I'll call it 9.2. Thank you. Feet per second. I made an error though.
Where?
When I moved this over, it should have been negative. And does it make sense that it should be negative?
Yeah, because you're falling down.
Well, I'm falling down. That's true. Sort of. Yes. Sure.
It's direct.
It isn't so much that I'm going down, but it's... How come this x was positive? Look at this x. This. Wait a minute.
The x is growing, the y is shrinking.
Thank you. The dx dt is positive. This dx dt is not negative,
right,
but it's going to the left. But it ain't about left and right. It ain't really about up and down. It's about what you said. You said, is the variable x growing?
Yes.
Then its rate of change is positive. Is the variable y decreasing? Then its rate of change is negative. Right. Yeah, good.
Okay, so that comes out.
So, that was kind of fun. It was really easy, but it's word problems. Students don't like word problems. But I'm trying to help you. I'm trying to help you think. It's not that hard. I don't think it's that hard. There's harder ones. Anyway, there's more. There's tougher ones in the book. There's some good ones we should work on next week, I guess. Okay. You know what? I think I'll just quit. My resignation letter in the morning. No, I didn't.